right now, at this very moment, something extraordinary is happening to the universe around you. As you sit there, completely unaware, the fabric of space itself is stretching. The distance between galaxies is growing. The cosmos is expanding in ways that scientists could not have imagined just a few decades ago. And the force driving this expansion is something so mysterious, so powerful, and so utterly invisible that we have given it a name that reflects our profound ignorance: dark energy. What if I told you that 68% of everything that exists in our universe is made of something we cannot see, cannot touch, cannot smell, cannot taste, and cannot detect with any instrument we have ever built? What if I told you that this invisible something is right now, at this very second, pushing the universe apart with a force greater than all the gravity of all the stars and all the galaxies and all the black holes combined? What if I told you that the ultimate fate of everything, every atom, every molecule, every star, every galaxy, every living thing that has ever existed or will ever exist, has already been determined by this mysterious force that we discovered only 26 years ago? This is not science fiction. This is not speculation. This is the reality we live in. Consider this mind-bending fact. Right now, galaxies at the edge of our observable universe are moving away from us faster than the speed of light. You might think this is impossible. You might think Einstein said nothing can travel faster than light, and you would be right. Nothing can travel through space faster than light. But here is the twist that will bend your mind. Space itself can expand at any rate it wants. There is no cosmic speed limit for the expansion of space, and so, distant galaxies are not traveling through space away from us. Instead, the space between us and them is stretching, growing, multiplying, and it is stretching so fast that light from those galaxies will never ever reach us. They are lost to us forever, and more galaxies are crossing this threshold every single day. Think about what this means. There are galaxies out there right now, with billions of stars, perhaps with planets, perhaps with civilizations, perhaps with beings looking up at their night sky, wondering about the universe, and they are being permanently disconnected from us. The light they are emitting right now will travel for billions of years, struggling against the expansion of space, and it will never arrive. It will never reach Earth. It will never be seen by any telescope we could ever build. These galaxies are being erased from our observable universe, one by one, silently and invisibly. And the force causing this cosmic vanishing act is dark energy. If this sounds incredible, if this sounds almost too strange to be true, then you are beginning to understand why dark energy is considered one of the greatest mysteries in all of physics. Scientists have spent decades trying to understand what dark energy is, and the honest truth is that we still do not know. We have theories, we have mathematics, we have observations. But the fundamental nature of this force that dominates our universe remains hidden from us. Today, I want to take you on a journey through space and time, through discovery and mystery, through the past and into the far future of our cosmos. I want to show you what dark energy is doing to space right now, how we discovered it, what we think it might be, and what it means for the ultimate fate of everything. This is going to be a deep dive, and I promise you, by the end, you will never look at the night sky the same way again. So if you are ready to explore one of the greatest mysteries the universe has ever presented to human minds, make sure you subscribe to this channel and hit that bell icon so you never miss another cosmic journey like this one. And I want to hear from you in the comments below. Do you think the universe will expand forever? Do you think dark energy will ultimately tear apart every atom in existence? Or do you think there is something we have not discovered yet that will change everything? Let me know your thoughts, and let us discuss this together as we journey through this incredible topic. Let us begin at the beginning. Not the beginning of the universe, but the beginning of our understanding. Let's go back to a time when humans thought they knew how the cosmos worked, and then let us watch that understanding shatter. In the early 20th century, the greatest mind in physics, Albert Einstein, was working on his masterpiece, the general theory of relativity. This theory described gravity not as a force pulling objects together, but as a curvature of space and time caused by mass and energy. Objects do not fall because gravity pulls them. They fall because massive objects like Earth curve the fabric of space-time, and objects naturally follow that curvature. It was a revolutionary idea, and it changed our understanding of the universe forever. But when Einstein applied his equations to the entire universe, he encountered a problem. According to his mathematics, the universe could not be static. It had to be either expanding or contracting. There was no stable middle ground. Matter curves space, and that curvature would inevitably cause everything to collapse together unless something was pushing it apart. Now, at that time, in 1917, everyone believed the universe was static and eternal. It had always existed, and it would always exist, unchanging and infinite. This was the common wisdom. This was what everyone assumed. So when Einstein's equations told him the universe could not be static, he did something that he would later call his greatest blunder. He added a term to his equations, a mathematical constant he called the Cosmological Constant, represented by the Greek letter lambda. This constant acted like a kind of anti-gravity, a force pushing space apart that exactly balanced the gravitational attraction of all the matter in the universe. With this addition, Einstein's equations allowed for a static universe, and he was satisfied. But the universe had other plans. In 1929, an astronomer named Edwin Hubble was working at the Mount Wilson Observatory in California, using the most powerful telescope of his time to observe distant galaxies. What he discovered would overturn everything scientists thought they knew about the cosmos. Hubble found that distant galaxies were not staying in one place, they were moving. And they were not moving in random directions. Almost every galaxy he observed was moving away from us. Even more astonishing, the farther away a galaxy was, the faster it was receding. Hubble had discovered that the universe was expanding. This was measured through something called redshift. When a light source moves away from you, the light waves get stretched out, shifting toward the red end of the spectrum. It is similar to how the sound of an ambulance siren drops in pitch as it drives away from you. By measuring the redshift of light from distant galaxies, Hubble could determine how fast they were moving away. And by comparing the redshift to the distance of each galaxy, which he estimated using certain types of stars as cosmic measuring sticks, he established a relationship that would become known as Hubble's law. The velocity at which a galaxy recedes from us is proportional to its distance from us. This was a staggering discovery. The universe was not static. It was not eternal and unchanging. It was dynamic, evolving, expanding. And if you mentally rewound the expansion, running the cosmic clock backward, you would find that all the galaxies would converge toward a single point. The universe had a beginning. There was a moment when everything that exists was compressed into an unimaginably hot, dense state, and then it exploded outward in what we now call the Big Bang. When Einstein heard about Hubble's discovery, he immediately recognized his error. The cosmological constant was not needed. The universe was not static. There was no need for a mysterious force pushing space apart to balance gravity. The universe was simply expanding, and that expansion was a natural consequence of the Big Bang. Einstein removed the cosmological constant from his equations and declared it his greatest blunder. But here is where the story takes a twist that nobody could have anticipated. Einstein was wrong about being wrong. For decades after Hubble's discovery, scientists studied the expanding universe with great interest. They understood that the Big Bang had set everything in motion, and that the universe had been expanding ever since. But they also understood that gravity, the attractive force between all massive objects, should be slowing this expansion down. Think of it like throwing a ball into the air. The ball leaves your hand with a certain velocity, but gravity immediately starts pulling it back, slowing it down. Eventually, the ball reaches its peak height and falls back to your hand. Scientists expected the universe to behave similarly. The Big Bang had given everything an initial outward velocity, but the gravitational attraction of all the matter in the universe should be decelerating that expansion. The only question was, by how much? Would gravity eventually stop the expansion and pull everything back together in a big crunch, the reverse of the Big Bang? Or was the expansion velocity too high, meaning the universe would expand forever, but more and more slowly, eventually coasting to a halt in the infinite future? This was the great debate in cosmology through the latter half of the 20th century. Scientists designed experiments to measure the deceleration of the universe to determine which fate awaited us. And in the 1990s, two teams of researchers set out to answer this question once and for all. The first team was called the Supernova Cosmology Project, led by Saul Perlmutter at the Lawrence Berkeley National Laboratory. The second team was called the High Z Supernova Search Team, led by Brian Schmidt and Adam Riess. These two teams were competitors, racing to measure the same thing: the rate at which the expansion of the universe was slowing down. Their method was ingenious. They used a particular type of exploding star called a Type 1a supernova as a cosmic measuring stick. Type 1a supernovae occur when a white dwarf star accumulates enough mass from a companion star to trigger a thermonuclear explosion. The remarkable thing about these explosions is that they all have approximately the same intrinsic brightness. They are what astronomers call standard candles. Because we know how bright they truly are, we can determine how far away they are by measuring how bright they appear to us. A supernova that appears dim is far away. A supernova that appears bright is nearby. By combining this distance measurement with the redshift of the supernova's host galaxy, which tells us how fast it is receding, scientists could map the expansion history of the universe. Both teams observed distant Type 1a supernovae, some of which had exploded billions of years ago, and compared their apparent brightness to their redshift. If the universe's expansion was decelerating, as everyone expected, then the supernovae should appear a certain amount brighter at a given redshift. The mathematics was straightforward. The observations were painstaking but achievable. Everyone knew what the answer should be, but the answer they got was impossible. In 1998, both teams announced their results, and they agreed with each other completely, which made the findings even more credible. The distant supernovae were not brighter than expected. They were dimmer. This meant they were farther away than expected, and the only way they could be farther away than expected was if the expansion of the universe was not slowing down at all. In fact, the expansion was speeding up. The universe was accelerating. This was like throwing a ball into the air and watching it fly upward faster and faster, defying gravity, defying everything we understand about how the universe should work. It made no sense. The gravitational attraction of all the matter in the universe should have been decelerating the expansion. Where was this extra push coming from? What force was powerful enough to overcome the gravity of every galaxy, every star, every particle in existence? The initial reaction from the scientific community was disbelief. Surely there was an error somewhere. Perhaps the supernova were not as reliable as standard candles. Perhaps dust in the universe was dimming the light. Perhaps there was some systematic mistake in the measurements. Both teams went back and checked their data again and again. They looked for every possible source of error, but the result held. The universe was accelerating and there was no getting around it. In 2011, Saul Perlmutter, Brian Schmidt and Adam Riess were awarded the Nobel Prize in Physics for this discovery. It was the most surprising and consequential cosmological finding since the Big Bang itself. And to explain it, scientists gave the mysterious force driving the acceleration a name that reflected their ignorance: dark energy. But why dark? The word dark in physics does not mean evil or sinister. It means invisible. It means undetectable by the electromagnetic radiation we use to observe the universe. We see the cosmos through light, visible light, infrared light, ultraviolet light, radio waves, X-rays, gamma rays. All of these are forms of electromagnetic radiation, and dark energy does not emit any of them. It does not absorb them either. It does not interact with light at all. We cannot see it, and we cannot photograph it. We can only detect its influence through its effect on the expansion of space. This is what makes dark energy so frustrating and so fascinating. It is the dominant component of our universe, making up approximately 68% of everything that exists, and yet it is completely invisible. We know it is there only because of what it does to the universe around us. So what is dark energy? What could possibly be causing this cosmic acceleration? This is the question that has consumed theoretical physicists for the past quarter century, and the honest answer is that we still do not know. But we do have some leading theories, some educated guesses, some mathematical frameworks that might explain what we're observing. Let me take you through them, and let us explore the possibilities together. The first and simplest explanation is that dark energy is exactly what Einstein proposed over a century ago, the cosmological constant. Remember, Einstein added this term to his equations to prevent the universe from expanding, and then he removed it when Hubble discovered that the universe was indeed expanding. But what if the cosmological constant is real? and it just has a different value than Einstein assumed. The cosmological constant can be thought of as the energy of empty space itself. This might sound paradoxical. How can empty space have energy? Is not empty space just nothing? But according to quantum mechanics, empty space is not nothing. It is a seething ocean of quantum fluctuations, with virtual particles constantly popping into and out of existence. These fluctuations are not just theoretical abstractions. They have been measured in laboratory experiments. The famous Casimir effect, for example, demonstrates that the quantum vacuum exerts a real, measurable force. If empty space has energy, then this energy would have a strange property. Unlike matter and radiation, whose energy density decreases as the universe expands because the same amount of stuff is spread over more volume, the energy density of the cosmological constant would remain the same no matter how much space expands. Every new cubic meter of space that appears would come with its own built-in energy. This is because the cosmological constant is a property of space itself, not something contained within space. And here is the key point. In general relativity, energy causes gravity. But the cosmological constant has a peculiar relationship with gravity. Its positive energy causes attractive gravity, as you would expect. But it also has negative pressure, and in general relativity, pressure also contributes to gravity. Either the negative pressure of the cosmological constant creates a repulsive gravitational effect that is 3 times stronger than the attractive effect of its energy. The net result is anti-gravity. Space pushes itself apart. This is why the cosmological constant causes accelerating expansion. As the universe expands, more space appears, and that space comes with its own dark energy, which causes even more expansion, which creates even more space and dark energy. It is a runaway effect, and it explains why the expansion of the universe is speeding up. The cosmological constant is mathematically the simplest explanation for dark energy. It fits the observations well. It is consistent with Einstein's equations, and ironically, Einstein's greatest blunder may turn out to be one of his greatest successes. But there is a problem, a very serious problem, and it is called the cosmological constant problem. If dark energy is the energy of the quantum vacuum, then we should be able to calculate its value using quantum field theory. And when physicists do this calculation, they get an answer. But it is the wrong answer. It is not just a little bit wrong. It is the most wrong prediction in the history of physics. The predicted value of the vacuum energy is larger than the observed value by a factor of 10 to the power of 120. That is a 1 followed by 120 zeros. If the cosmological constant were actually this large, the universe would have expanded so rapidly in its first fraction of a second that no stars, no galaxies, and no life could ever have formed. Clearly, something is deeply wrong with our understanding. This discrepancy is known as the vacuum catastrophe, and it remains one of the great unsolved problems in theoretical physics. Either our calculation of the vacuum energy is fundamentally flawed, or there is some unknown mechanism that cancels out most of this energy, leaving behind just a tiny residual that we observe as dark energy. But we have no idea what that mechanism might be. So while the cosmological constant remains the leading candidate for dark energy, we must acknowledge that we do not understand why it has the value it does. We can measure it, but we cannot explain it. The second major theory for dark energy is called quintessence. Unlike the cosmological constant, which is a fixed value built into the fabric of space, quintessence is a dynamic field that changes over time. The name comes from the ancient Greek concept of the fifth element, the ethereal substance that filled the heavens beyond the earth. In the quintessence model, dark energy is carried by a scalar field that pervades all of space. This field has energy and pressure, and under certain conditions its pressure can be negative, causing accelerating expansion just like the cosmological constant. But unlike the cosmological constant, the properties of quintessence can evolve as the universe ages. The strength of the acceleration could change over time. It could have been weaker in the past and stronger now, or it could be weakening as we speak. This possibility is actually quite important because it makes quintessence testable. If dark energy is truly the cosmological constant, then its density has been the same throughout cosmic history and will remain the same forever. But if dark energy is quintessence, then its density could be changing, and we might be able to detect that change by comparing the expansion rate of the universe at different epochs. There are many variants of quintessence, with names like tracker quintessence, K-essence, and phantom energy. Some of these models have the dark energy weakening over time, eventually allowing gravity to take over and possibly leading to a big crunch after all. Others have the dark energy strengthening, leading to a catastrophic scenario we will discuss later called the Big Rip. The observations we have so far are consistent with both a constant dark energy and one that is slowly changing. We need more data to tell the difference. The third possibility is that dark energy does not exist at all. What if there is no mysterious force pushing space apart? What if, instead, our theory of gravity is simply incomplete? General relativity has been tested to exquisite precision in many contexts. The orbit of Mercury, the bending of light around the sun, the gravitational waves emitted by merging black holes. In all these tests, Einstein's theory has performed flawlessly, but all of these tests have been conducted on relatively small scales: planets, stars, even individual galaxies. What if general relativity breaks down when applied to the entire universe? What if the rules of gravity change at cosmological distances? This idea is called modified gravity, and there are many different proposals for how gravity might be modified. Some theories, like those in the F-registered class, add extra terms to Einstein's equations that become important only at large distances. Others propose extra dimensions of space that alter gravitational behavior. Still others suggest that gravity is not a fundamental force at all, but an emergent phenomenon arising from more basic thermodynamic or information-theoretic principles. The physicist Eric Verlinde has proposed a particularly radical idea along these lines. He suggests that gravity is an entropic force, similar to the pressure that causes a gas to expand. In this view, what we perceive as dark energy might not be a new form of energy at all, but rather a consequence of the entropic nature of gravity, operating in ways we do not yet understand. Modified gravity theories are attractive because they do not require us to postulate an entirely new form of energy that has never been detected. But they face their own challenges. Any modification to general relativity must still be consistent with all the successful tests of Einstein's theory. It must explain not only the acceleration of the universe, but also other cosmological observations like the cosmic microwave background and the formation of large-scale structures. So far, no modified gravity theory has been able to do all of this as successfully as dark energy models. The truth is, we simply do not know what dark energy is. We have theories, we have mathematics, we have data, but we do not have a complete answer. This is one of the most profound mysteries in all of physics, and solving it will likely require new insights that we cannot currently imagine. But while we do not know what dark energy is, we do know what it is doing, right now, at this very moment, and that is what I want to focus on next. Let me paint a picture for you of what is happening to the universe as you read these words. Space is stretching, not just in some abstract mathematical sense, but in a very real, physical sense. The distance between any 2 points in the universe that are not gravitationally bound together is increasing. This is not like an explosion, where matter flies outward through a pre-existing space. This is the space itself getting larger. It is as if the very fabric of reality is being pulled apart from within. To understand this, consider the famous analogy of the raisin bread. Imagine you are baking a loaf of raisin bread. Before baking, the raisins are scattered throughout the dough, each one separated from its neighbors by a certain distance. Now, as the bread bakes, the dough expands. Every raisin sees every other raisin moving away from it, not because the raisins are moving through the dough, but because the dough itself is expanding. A raisin near one end of the loaf sees nearby raisins moving away slowly, and distant raisins moving away quickly. The farther away a raisin is, the more dough there is between you, and the faster that dough is expanding. This is exactly what is happening to galaxies in our universe. The galaxies are like the raisins, and the fabric of space is like the dough. Every galaxy sees every other galaxy moving away from it, with more distant galaxies receding faster. This is Hubble's law. Velocity equals distance times the Hubble constant. But unlike the raisin bread analogy, which involves a finite loaf that expands to a larger finite size, the universe appears to be infinite, and it has been expanding forever. There is no center of the expansion. Every point in the universe can consider itself the center. Every galaxy is being carried along by the expansion of space, and from every galaxy's perspective, all other galaxies are flying away. Now here is where dark energy comes in. If gravity were the only force acting on the expansion would be slowing down. The mutual gravitational attraction of all the matter in the universe would be decelerating the outward motion, like friction slowing a car. And for the first several billion years of the universe's history, this is exactly what happened. The expansion was decelerating, gravity was winning. But about 5 billion years ago, something changed. The density of matter in the universe, which decreases as space expands because the same amount of matter is spread over more volume, dropped below a critical threshold. At that point, the density of dark energy, which stays constant as space expands, became dominant. Dark energy took over, and instead of slowing down, the expansion started speeding up. We are now living in the era of cosmic acceleration. The expansion of the universe is no longer decelerating, it is accelerating, and it has been accelerating for the past 5 billion years. What does this mean in practical terms? It means that the rate of expansion is getting faster and faster. Right now, the Hubble constant, which measures the current expansion rate, is approximately 70 kilometers per second per megaparsec. This means that for every megaparsec of distance, which is about 3.26 million light-years, the expansion velocity increases by about 70 kilometers per second. A galaxy 1 megaparsec away is receding from us at 70 kilometers per second. A galaxy 2 megaparsecs away is receding at 140 kilometers per second. A galaxy 100 megaparsecs away is receding at 7,000 kilometers per second. And here is the astonishing part. If you go far enough, you reach a distance where the recession velocity equals the speed of light. Beyond that distance, galaxies are receding faster than light. And beyond an even greater distance, the space between us and those galaxies is expanding so fast that light emitted from them right now will never reach us. This is the cosmic event horizon, and it marks the boundary of what we can ever hope to observe. You might be wondering how galaxies can move faster than light if nothing can exceed the speed of light. This is a subtlety that trips up many people. Einstein's special relativity says that nothing can travel through space faster than light. But the expansion of the universe is not movement through space. It is the expansion of space itself, and there is no speed limit for that. Space can expand at any rate it wants, carrying galaxies along with it, and there is no violation of relativity. Right now, the cosmic event horizon is at a distance of about 16 billion light-years, and the galaxies beyond this horizon are receding faster than light, and we will never receive any signal from them, no matter how long we wait. And because the universe is accelerating, this horizon is getting closer. More and more galaxies are crossing the threshold into eternal invisibility. Let me give you a concrete sense of what this means. The Andromeda galaxy, our nearest large neighbor, is actually moving toward us because we are gravitationally bound to it. We will merge with Andromeda in about 4.5 billion years, but most other galaxies are moving away. The Virgo cluster, a massive collection of galaxies about 50 million light-years away, is receding from us at about 1,000 kilometers per second. The Coma cluster, about 300 million light-years away, is receding at about 7,000 kilometers per second. Now consider very distant galaxies, those we observe with the Hubble Space Telescope and the James Webb Space Telescope at the edge of the observable universe. Some of these galaxies are so far away that the light we see left them over 13 billion years ago, when the universe was less than 1 billion years old. But because space has been expanding all this time, those galaxies are now much farther away than 13 billion light-years. In fact, the current distance to the edge of the observable universe is about 46 billion light-years. And many of the galaxies we see in the distant universe have already crossed the cosmic event horizon. The light they are emitting right now will never reach us. We are seeing them as they were billions of years ago, but we will never see what they become. This is what dark energy is doing to space right now. It is stretching the fabric of the cosmos, pushing galaxies apart, accelerating the expansion, and slowly erasing the most distant regions of the universe from our view. It is a silent, invisible force that is reshaping the cosmos on the grandest scale imaginable. And it is not just affecting distant galaxies, it is affecting the entire structure of the universe. Consider what happens to photons, the particles of light, as they travel across an expanding universe. A photon emitted from a distant galaxy begins its journey toward us, traveling at the speed of light. But as it travels, space is expanding. The photon is like a swimmer trying to cross a river that is getting wider as she swims. She's making progress, moving through the water. But the destination keeps getting farther away. For photons from most of the observable universe, they still reach us eventually, but it takes longer than it would in a static universe. The photon's wavelength gets stretched as space expands, shifting it toward the red end of the spectrum. This cosmological redshift is different from the Doppler shift caused by motion through space. It is a stretching of the light wave itself, caused by the expansion of the medium through which the light travels. By measuring the redshift of light from distant objects, we can determine how much the universe has expanded since that light was emitted. A galaxy with a redshift of 1 has had its light stretched to twice its original wavelength, meaning the universe has doubled in size since that light left the galaxy. The most distant galaxies we observe have redshifts of 10 or more, meaning the universe has expanded by more than a factor of 11 since their light began its journey. But for photons emitted beyond the cosmic event horizon, the situation is even more extreme. These photons are indeed traveling toward us at the speed of light, but the space between us and them is expanding faster than the speed of light. It is like running on a treadmill that is accelerating. No matter how fast you run, you can never reach the end because the treadmill keeps speeding up. These photons will travel forever, losing energy as their wavelengths stretch to infinity, but they will never arrive. The galaxies that emitted them are forever beyond our reach. Now let me ask you a question. Does dark energy affect you? Does it affect our solar system, our galaxy, our everyday lives? The answer is almost not at all. And the reason is that dark energy is incredibly weak at small scales. Remember, dark energy has a constant density throughout space, approximately 70% of the total energy density of the universe. But the total energy density of the universe is incredibly low, about the equivalent of 6 hydrogen atoms per cubic meter. 70% of almost nothing is still almost nothing. The dark energy in a cubic meter of space is equivalent to the mass of a few hydrogen atoms. Compare this to the density of matter on Earth, which is about 30 orders of magnitude higher, or compare it to the density of the Milky Way galaxy, which is 1,000 times higher than the cosmic average. At these scales, the gravity of ordinary matter completely overwhelms the effect of dark energy. That is why the Earth stays in orbit around the Sun, why the Moon stays in orbit around the Earth, why the Milky Way stays gravitationally bound as a single galaxy. Dark energy only becomes important when you consider distances so large that the density of matter becomes comparable to the cosmic average. At the scale of galaxy clusters and larger, where the average density is low enough, dark energy's constant push becomes significant. At smaller scales, gravity wins. At larger scales, dark energy wins. This is why our solar system is not being torn apart by dark energy. The gravitational binding energy of the solar system is vastly greater than the dark energy within it. The same is true for our galaxy and for the local group of galaxies, which includes the Milky Way, Andromeda, and about 80 smaller galaxies. These systems are gravitationally bound and will remain so. They will not be pulled apart by the expansion of space. But beyond the local group, dark energy rules. Every other galaxy cluster is being pushed away from us by the expansion of space, and that expansion is accelerating. The Virgo cluster, the Coma cluster, the great superclusters that stretch across hundreds of millions of light years, all of them are receding faster and faster. So what does the future hold? What will dark energy ultimately do to the universe? This is where we venture into the realm of cosmic fate, and the answer depends on the true nature of dark energy. If dark energy is indeed the cosmological constant, a fixed property of space that never changes, then the universe faces what physicists call the Big Freeze, also known as the heat death of the universe. This is the most likely scenario based on our current understanding, and it is both awe-inspiring and deeply melancholic. Let me walk you through the timeline. Right now, we're about 13.8 billion years after the Big Bang. Stars are being born in galaxies throughout the universe. Our sun is about halfway through its life, with another 5 billion years before it becomes a red giant and then a white dwarf. The universe is vibrant and dynamic, full of light and energy and, in at least one place, life. Fast forward 100 billion years. The expansion of the universe has continued accelerating. By now, every galaxy outside our local group has crossed the cosmic event horizon. If intelligent beings still exist at that time, they will look up at the night sky and see only the stars of their own merged galaxy. The combination of the Milky Way and Andromeda and the other local galaxies into one giant elliptical galaxy that some have nicknamed Milkomeda They will see no other galaxies. They will have no evidence that any other galaxies exist. From their perspective, the universe will appear to be just one galaxy in an infinite void. This is profoundly disturbing. Future astronomers will have no way of knowing that the universe was once filled with hundreds of billions of galaxies. All the evidence will be gone, carried away by the expansion of space. They might develop a cosmology that has nothing in common with ours, because the data available to them will be completely different. This is one of the strange gifts of living in our current epoch. We can see the true extent of the universe. Future civilizations may not be so lucky. Continue forward to 1 trillion years, 1,000 billion years. By now, star formation has essentially ceased. All the gas and dust that fuels the birth of new stars has been used up or dispersed. The last stars, small red dwarfs that burn their fuel slowly and efficiently, are still shining, but their days are numbered. No new stars are being born to replace those that die. At 100 trillion years, the last stars burn out. The universe enters what is called the degenerate era. All that remains are stellar remnants, white dwarfs, neutron stars, and black holes. There are also planets that have escaped their stars drifting through the darkness. And there are brown dwarfs, failed stars that never ignited nuclear fusion. The universe is cold and dark, with no natural sources of light except the faint glow of cooling white dwarfs. But even the white dwarfs will not last forever. Over incredibly long timescales, measured in trillions of years, gravitational interactions will slowly unbind galaxies. Stars and stellar remnants will either be ejected into intergalactic space or fall into the central black holes of their galaxies. The universe becomes a vast, nearly uniform sea of particles, with occasional black holes scattered throughout. And then there are the black holes themselves. For a long time, scientists thought black holes were eternal, that nothing could ever escape them. But Stephen Hawking showed in the 1970s that black holes do emit radiation through a quantum process. This Hawking radiation is incredibly faint for stellar and supermassive black holes, so faint that it would take unimaginable eons for them to evaporate. But given enough time, even the largest black holes will radiate away all their mass and disappear in a final burst of energy. The evaporation time for a supermassive black hole with the mass of 1 billion suns is about 10 to the power of 100 years. That is one followed by 100 zeros, a number so large that there is no analogy that can make it intuitive. For comparison, the current age of the universe is about 10 to the power of 10 years, a mere one followed by 10 zeros. The black hole era will last unimaginably longer than the stellar era that preceded it. After the black holes evaporate, all that remains are the elementary particles scattered through an ever-expanding void. Electrons, positrons, neutrinos, and photons with wavelengths stretched to cosmic scales by the expansion of space. The universe asymptotically approaches absolute zero maximum entropy, a state of perfect thermodynamic equilibrium from which nothing interesting can ever emerge again. This is the heat death of the universe. Not a fiery explosion, not a dramatic collapse, but a slow, gradual fading into eternal cold and darkness. It is the universe running out of usable energy, becoming a uniform soup of extremely low-temperature particles that can never again coalesce into stars or galaxies or life. If the cosmological constant is truly constant, this is the fate that awaits us. The expansion will continue forever, accelerating forever, pushing everything apart until even the memory of the universe's vibrant past is erased by the relentless dilution of energy. But there is another possibility, a more dramatic and terrifying one, and it depends on whether dark energy might be getting stronger. Remember Quintessence, the idea that dark energy is a dynamic field that can change over time. One variant of Quintessence is called phantom energy, and it has a peculiar property. In phantom energy models, the energy density of dark energy increases as the universe expands, rather than staying constant. This might seem impossible, since more space should mean the same amount of energy spread thinner. But phantom energy violates this intuition. It has an equation of state parameter, usually called W, that is less than -1. For the cosmological constant, Q equals exactly -1. For phantom energy, Q is less than -1, meaning the negative pressure is so extreme that it actually creates more energy as space expands. If phantom energy is real, then the acceleration of the universe will not just continue, it will intensify, getting faster and faster at an ever-increasing rate, and eventually the expansion will become so extreme that it will overcome not just the gravity holding galaxy clusters together, but also the gravity holding individual galaxies together, then solar systems, then planets, then atoms themselves. This scenario is called the Big Rip, and it is one of the most violent fates imaginable for the universe. Let me walk you through the timeline of a Big Rip, assuming current observations and a specific model for phantom energy. Billions of years before the rip, the effects are subtle. Galaxy clusters start to dissociate, their member galaxies drifting apart faster than gravity can hold them. The universe still looks relatively normal, but the seeds of destruction have been planted. About 60 million years before the rip, the Milky Way itself begins to feel the effects. The expansion rate within our galaxy becomes comparable to the gravitational forces holding it together. Stars start to drift away from the galactic center. The familiar spiral structure dissolves. About 3 months before the rip, the solar system dissociates. The sun can no longer hold on to its planets. Earth drifts away into space, freed from its orbital embrace. Of course, by this point the sun has already evolved into a white dwarf, so this is a moot point for any life that might have once existed here. About 30 minutes before the rip, Earth itself is destroyed. The expansion rate becomes so extreme that the planet can no longer hold itself together. The rock and metal that make up our world are pulled apart, disintegrating into rubble. In the last fraction of a second, atoms are torn apart. Electrons are ripped away from nuclei. Atomic nuclei are torn apart into protons and neutrons, and then protons and neutrons themselves are torn apart into quarks. The fundamental structure of matter is destroyed. At the moment of the Big Rip, the scale factor of the universe becomes infinite. This is a mathematical singularity, a point where the equations break down and we cannot predict what happens next. It is the end of space as we know it, the end of time as we know it, the end of everything. Now, I should emphasize that the Big Rip is not the most likely scenario based on current observations. The best data we have suggests that W is very close to -1, consistent with the cosmological constant. But the uncertainty in these measurements is large enough that phantom energy cannot be ruled out. Future observations with more precise measurements of the expansion history of the universe will help us determine whether the Big Rip is a real possibility or just a theoretical curiosity. There are other fates that have been proposed for the universe, though they are generally considered less likely than the Big Freeze. The Big Crunch, the reverse of the Big Bang, would occur if the expansion eventually stops and reverses. All the matter in the universe would fall back together, compressing into a smaller and smaller volume until it reaches a state of infinite density. This was a serious contender before the discovery of dark energy, but now that we know the expansion is accelerating, the Big Crunch seems unlikely unless dark energy somehow switches off or reverses. The Big Bounce is a speculative extension of the Big Crunch, in which the universe collapses but then bounces back, initiating a new Big Bang. This would create an endless cycle of universes, expanding, contracting, and rebounding. There are some theoretical models that support this idea, but they remain highly speculative. The Big Slurp is perhaps the most unsettling possibility. It has to do with the stability of the Higgs field, the field that gives particles their mass. Physicists have calculated that the Higgs field might be in a metastable state, meaning it is stable for now, but could potentially decay to a lower energy state. If this happened, a bubble of true vacuum would form somewhere in the universe and expand at nearly the speed of light, destroying everything in its path. Inside the bubble, the laws of physics would be different. Atoms as we know them might not exist. Life would certainly be impossible. The unnerving thing about the Big Slurp is that it could happen at any moment with no warning. We would never see it coming because the bubble expands at the speed of light. One moment we would exist, and the next moment we would not, replaced by an utterly alien form of space-time. However, most physicists believe that even if the vacuum is metastable, its lifetime is far longer than the current age of the universe, probably longer than the time it takes for all the stars to burn out. So the Big Slurp, while theoretically possible, is not something we need to worry about in any practical sense. Given all these possibilities, what is the most likely fate of the universe according to our current best understanding? The answer is the Big Freeze, the slow heat death driven by the cosmological constant. The expansion will continue forever, accelerating forever. Galaxies will disappear beyond the cosmic horizon. Stars will burn out. black holes will evaporate, and the universe will approach a state of maximum entropy, devoid of structure, devoid of energy gradients, devoid of the potential for anything interesting to ever happen again. This is the future that dark energy is writing for us right now, at this very moment, as space stretches and galaxies recede, and the cosmos slowly, inexorably, fades into eternal darkness. But let us step back from these far future scenarios and return to the present. What are scientists doing right now to understand dark energy better? What new observations and experiments are revealing about this mysterious force? The past few years have seen remarkable advances in our ability to probe dark energy, thanks to a new generation of telescopes and surveys that are mapping the universe with unprecedented precision. One of the most exciting recent developments comes from the Dark Energy Spectroscopic Instrument, or DESI, which began its 5-year survey in 2021. DESI is mounted on the Mayall telescope at Kitt Peak National Observatory in Arizona, and it is designed to create the most detailed three-dimensional map of the universe ever made. It does this by measuring the redshifts of tens of millions of galaxies and quasars, thus building up a picture of the large-scale structure of the cosmos that reveals how the expansion rate has changed over the past 11 billion years. The early results from DESI have been tantalizing. In 2024 and 2025, the DESI collaboration released data that hint at something remarkable. Dark energy might not be constant after all. The observations are consistent with dark energy having been weaker in the past and getting stronger over time. If confirmed, this would rule out the simple cosmological constant and point toward quintessence or some other dynamic form of dark energy. Now, I must be careful here because these results are preliminary, and the statistical significance is not yet conclusive. Scientists are cautious by nature, and they will not declare a discovery until the evidence is overwhelming. But the possibility that dark energy is changing is exciting precisely because it would give us a new window into its nature. A changing dark energy leaves fingerprints in the expansion history of the universe that we can measure and study. A truly constant dark energy tells us almost nothing about what it is. The James Webb Space Telescope, which began its scientific operations in 2022, has also contributed to our understanding of dark energy, though indirectly. JWST is designed primarily to study the early universe and the formation of the first galaxies, but its observations have revealed some surprises that bear on cosmology. One surprise is the presence of unexpectedly massive and bright galaxies in the very early universe, just a few 100 million years after the Big Bang. According to standard cosmological models, galaxies should have taken longer to grow so large. Finding these early giants suggests that either galaxies formed faster than we thought, or there is something wrong with our models of the early universe. Some researchers have speculated that dark energy might have behaved differently in the early universe, though this remains highly speculative. JWST has also contributed to what is known as the Hubble tension, a discrepancy between different measurements of the current expansion rate. When astronomers measure the Hubble constant using observations of the local universe, such as Cepheid variable stars and Type 1a supernovae, they get a value around 73 kilometers per second per megaparsec. But when cosmologists calculate the Hubble constant based on observations of the cosmic microwave background and the standard cosmological model, they get a value around 67 kilometers per second per megaparsec. This 6% discrepancy might not sound like much, but the measurements are precise enough that the difference is statistically significant. Something is wrong. Either there is some systematic error in one or both measurements, or our cosmological model is missing something important. And some researchers have suggested that the missing piece might be related to dark energy. Perhaps dark energy behaved differently at different epochs, in a way that would reconcile the two measurements. Or perhaps there is a form of early dark energy that affected the early universe and then faded away. The European Space Agency's Euclid mission, launched in 2023, is specifically designed to study dark energy by mapping the geometry of the universe over the past 10 billion years. Euclid uses two primary techniques: weak gravitational lensing, which measures how the light from distant galaxies is bent by the matter between us and them, and galaxy clustering, which reveals the large-scale structure of the cosmos. By combining these measurements, Euclid will constrain the properties of dark energy with unprecedented precision. As of my knowledge, Euclid has been collecting data, and early results have been released, though the full scientific harvest will take several more years. but the potential is enormous. If dark energy is changing over time, Euclid should be able to detect it. If dark energy is truly constant, Euclid will confirm that with high confidence. Either way, we will know more about the nature of the force that dominates our universe. Looking further ahead, the Vera C. Rubin Observatory in Chile is preparing for its legacy survey of space and time, a 10-year survey that will image the entire visible sky every few nights. This survey will discover millions of Type 1a supernovae, vastly increasing the sample available for cosmological studies. It will also measure weak gravitational lensing with exquisite precision. The combination of these data will place tight constraints on dark energy and may reveal whether it is truly constant or evolving. The Nancy Grace Roman Space Telescope, scheduled to launch later this decade, will add another powerful tool to our arsenal. With a field of view 100 times larger than Hubble's, Roman will survey the sky for Type 1a supernovae and measure the large-scale structure of the universe with a precision that rivals Euclid. And on the ground, new cosmic microwave background experiments like CMB-S4 will measure the afterglow of the Big Bang with such precision that they will be sensitive to subtle effects of dark energy in the early universe. What all these experiments have in common is a drive to answer the fundamental questions about dark energy. Is it truly constant, the cosmological constant that Einstein proposed and then rejected? Or is it dynamic, changing over time like quintessence? Or is it something else entirely, perhaps a sign that our theory of gravity needs to be modified? Within the next decade, we should have much better answers to these questions. The data from DESI, Euclid, Rubin, Roman, and CMB-S4 will either confirm our current best model or point towards something new. Either outcome would be profoundly important. Confirming the cosmological constant would deepen the mystery of why it has the value it does. Discovering that dark energy changes would open a new frontier in physics, revealing that the universe is even stranger than we thought. Let me now step back and reflect on what all of this means, not just for physics, but for us as human beings contemplating our place in the cosmos. Dark energy tells us something profound about the universe we live in. It tells us that most of what exists is invisible and mysterious. It tells us that the cosmos is not static and eternal, but dynamic and evolving with a beginning and, in some sense, an end. It tells us that the forces shaping the universe operate on scales so vast that human intuition fails us completely. And yet, here we are, tiny beings on a small planet orbiting an average star in a typical galaxy, and we have figured out that dark energy exists. We have measured its effects. We have constrained its properties. We have contemplated its implications for the fate of everything. This is remarkable. This is what it means to be human, to look up at the night sky, to wonder what is out there, and to find answers that are more surprising and more beautiful than anything we could have imagined. There is a deep irony in our cosmic situation. We are living in a special time, a window of opportunity in the history of the universe. Right now, we can see hundreds of billions of galaxies. We can observe the cosmic microwave background, the afterglow of the Big Bang. We can trace the expansion history of the universe back to its earliest moments. We have access to a wealth of cosmological information that will not be available to future civilizations. In a few 100 billion years, when all the other galaxies have receded beyond the cosmic horizon, future astronomers will have no way of knowing what the universe once looked like. They will see only their own galaxy, isolated in an apparently infinite void. They might develop a cosmology that describes a static, unchanging universe, because that is what the evidence will suggest. The very existence of the Big Bang, of the cosmic microwave background, of the hundreds of billions of galaxies that we can see today, will be beyond their ability to discover. This means that we, the inhabitants of this particular epoch, have a responsibility. We are witnesses to a universe that will soon become invisible. We are the record keepers of cosmic history. The knowledge we have gained about dark energy, about the expansion of the universe, about the origin and fate of all things, this knowledge will become irretrievable in the far future. We are living in the golden age of cosmology, and we may be the only ones who will ever see the universe as it truly is. Does it matter that the universe will eventually fade into eternal darkness? Does it matter that, in the far future, no stars will shine, no galaxies will glow, no life will stir? Different people will have different answers to this question, but I believe there is meaning in the asking. The universe is not required to care about us. It is not required to provide purpose or permanence, and yet, within this vast, indifferent cosmos, something extraordinary has happened. Matter has organized itself into structures that can wonder about their own existence. Atoms have arranged themselves into brains that can contemplate the atoms. The universe has developed, in at least one small corner, the capacity to understand itself. This is precious even if it is temporary, perhaps especially because it is temporary. Dark energy will continue to do what dark energy does. It will stretch space, accelerate the expansion, push galaxies beyond the horizon. It will drive the universe toward its ultimate fate, whatever that turns out to be. This process is beyond our control. We cannot stop it, cannot slow it, cannot reverse it. But we can understand it. We can map it. We can measure it. We can write down equations that describe it and build instruments that probe it. We can look out at the universe, see the evidence of dark energy at work, and feel the profound privilege of being alive at a time when such understanding is possible. And perhaps, in the end, that is enough. Perhaps the meaning of existence is not found in permanence, but in the act of witnessing, in the brief flicker of consciousness that arises from the cosmic dust and contemplates the cosmos from which it came. We are the universe experiencing itself. We are dark energy's observers, and for this brief moment, before the stars go out and the darkness takes hold, we have the chance to see, to understand, to wonder. That is what dark energy is doing to space right now. It is stretching the fabric of reality, accelerating the expansion of the cosmos, determining the fate of everything that exists. It is the dominant component of the universe, and yet it remains one of the deepest mysteries we have ever encountered. We have journeyed from the discovery of the expanding universe by Hubble, through Einstein's cosmological constant and his greatest blunder that may not have been a blunder after all, through the shock of discovering that the expansion is accelerating, through the theories about what dark energy might be, through the effects it is having on the cosmos right now, through the possible fates of the universe in the far future, and through the cutting-edge research that is probing this mystery as we speak. The story is not over. In fact, it is just beginning. We are living in the era when dark energy was first discovered, when the first constraints on its properties were measured, when the first hints of its possible evolution were glimpsed. Future generations will know more than we do. They will have better data, better theories, perhaps a complete understanding of what dark energy truly is. Or perhaps they will not. Perhaps dark energy will remain mysterious for centuries or millennia. Perhaps understanding it will require a revolution in physics that we cannot currently imagine. Perhaps it is a clue to the nature of space and time themselves, a hint that the universe is far stranger than our current theories suggest. Whatever happens, I am grateful to be alive at this moment, when we can look up at the night sky and know that we are seeing something that will one day be invisible. When we can measure the expansion of the universe and know that it is accelerating, when we can ask the question, what is dark energy, even if we cannot yet answer it. And so, as I conclude this exploration of what dark energy is doing to space right now, I want to leave you with a thought. The universe is vast beyond comprehension. It contains more stars than there are grains of sand on all the beaches of Earth. It has been evolving for nearly 14 billion years, and it will continue evolving for trillions of years to come, perhaps for eternity. And most of it, 68% of it, is made of something we cannot see and do not understand. Yet here we are, on our little planet, in our little solar system, in our little galaxy, figuring it out. We have built telescopes that can see to the edge of the observable universe. We have developed theories that explain the behavior of matter and energy at scales from the subatomic to the cosmic. We have discovered dark energy and measured its effects. We have contemplated the fate of all existence. This is the human adventure. This is what makes us remarkable. Not our size, not our lifespan, not our place in the cosmos, but our ability to understand, to wonder, to reach beyond our limitations and grasp something of the truth. Dark energy is doing something to space right now. It is stretching it, expanding it, accelerating it toward an uncertain future. And we, for this brief moment in cosmic history, are here to witness it. If you have made it this far, thank you for joining me on this journey. I hope you have gained some understanding of what dark energy is, what it is doing, and what it means for the future of the universe. If you enjoyed this exploration, Please subscribe to the channel and hit that notification bell so you do not miss our future deep dives into the mysteries of the cosmos. Leave a comment below sharing your thoughts. What do you think dark energy is? What do you think the fate of the universe will be? What questions do you have about what we have discussed? And most importantly, keep looking up. Keep wondering. Keep asking questions. The universe is stranger and more beautiful than we can imagine, and understanding it is the greatest adventure of all. Stay curious, stay amazed, and I will see you in the next cosmic journey. End.